So now I start. So previously, what I am talking that if you design the combinational circuits by using the minimized expressions or the optimized logic expressions using the logic gates and the connecting wires, that is called interconnections, then what happens? The power dissipation, the delay and the heat and as well as the noise will be incorporated in the circuit. So for this reason, we come to the digital IC, that is called integrated circuits. These integrated circuits are mainly designed with some logic families or the logic technologies. The same logic design using the same type of ICs. So that is why the logic family name come. Logic family means in a family where the same type of operations or same type of electrical parameters, electrical designs are there and the fabrication procedures also there, same type of all over the all ICs. So they're in a same logic, that is called the logic family. So in this lecture, we want to discuss the introduction of the logic family, classification of the ICs, characteristics of the logic families of the digital ICs, transistor as a switch, classification of logic families, and the familiar with the digital ICs under the logic family. So how I will know, we will know that the IC incorporated in which logic family. So there are so many logic families are there. I will come in detail. So first, the introduction of the logic family. The digital logic is concerned with the interconnection, which I already told, among the digital components, just like a logic gates and some modules. The best known example of a digital system is the general purpose digital computer. This is the best known digital system. Most of the digital circuits are constructed on a single chip to reduce the area, to reduce the power dissipation, to reduce the delay, and also immune the noise. So this is very much important to us, that digital circuits are constructed on a single chip. Now the SoC exists in the market, is available in the market. SoC means system on chip. Total system is in the chip, single chip. So the power dissipation is very less, which are referred to as the integrated circuit. So these are the advantages, but there is some disadvantages also of the ICs. What are there? The digital ICs are only available for the low power design purposes. It cannot handle the high power. In low temperature, it will act. And another thing is that the very much large electrical circuits like the transformers, like the coils, like the inductors are not fabricated in a single chip. So these are the very much disadvantage of the ICs. But we should go for the simple ICs due to the less area, less power, high speed, and the high noise immunity. So the different circuit configurations and the production technologies are used during the production of the digital integrated circuits. Each of these approaches called the specific logic families. Now the idea of having different approaches or the different logic families is that each IC of the same family, when fabricated, will have the identical electrical characteristics. This is the very much important. This is the very much important parameters of the logic family. Identical electrical characteristics of each of the logic family. The characteristics which are bound to be identical are the supply voltage, which are the parameters, which should be identical. The supply voltage range, speed of response, dissipation of power, input and output logic levels, current sinking capability, and the current sourcing capability, noise margin, fan out, etc. I will discuss it later elaborate. Now, what is the significance of the logic families? When we talk about the digital systems, actually the digital ICs are the ones which make up the whole system. If we want to make a system, then we should use some different types of digital ICs with some interconnections. Now, if all the ICs are in same logic family, then they are compatible to each other, and the intended logic functions are performed and goal is achieved. So if we use the same logic family ICs, then it will be very much easier to design our circuits, or the electrical parameters are the same for the all ICs. The VCC power supply should be the same of the all ICs. But in case of ICs belonging to the different logic families are used in a digital system, then to ensure the compatibility of the interfacing techniques must be used. And that is the reason why we must understand the different logic families and use the best combination of ICs during the design of a digital system. For this reason, we should understand the different types of logic families. Now the question arises, what might be the consequence of the choosing wrong combination of ICs? The answer is, it may not match the necessary capability which you have needed. So for this reason, the same type of logic families ICs should be used. But the Moore's law predict that in 1965, co-founder of the Intel, Moore, a number of transistors to be double in every 2 years in a single chip IC. So as per this graph, we get that in 2000, we will get the more than 10 crore, more than 10 crore number of transistors used in a single chip. That is called Pentium 4 processor. So if we use more number of transistors in a single chip, then there is some problem needed occur, because the size of the device is scaled down. Hope you already know the scaling effect of the MOSFET in solid state devices. So short channel effect or the scaling effects. So that will be the effect where we should consider to design the logic ICs using the MOSFETs or the transistors. So based on the level of integration, the ICs are classified as integration means the number of gates per chip. How many number of gates are used or incorporated or integrated in a single chip? That is the parameter on which the ICs are classified like this. Small scale integration or SSI, where the less than number of 12 gates are in a single chip. Example, AND gate, OR gate, NOT gates, etc. Medium scale integration, MSI, 12 to 99. The example is adders, decoders, counters, flip-flops, and the multiplexers. Large scale integration, LSI, where the number of gates are 100 to 9999. The IO chips, memory, arithmetic, and the logic units are the examples. Very large scale integration where the 10,000 to 99,000 number of gates in a single chip. That is called processors. Large memory array and the programmable logic devices, microprocessor chips, microcontrollers, basic PICs, and the calculators. But now we use the ultra large scale integration or ULSI, where the number of gates are more than 1 lakh. The CPU, GPUs, and the video processors, microcontrollers, FPGAs, and the complex PICs are used. Okay, so these are the based on the level of integration. How many number of gates are integrated in a single chip? And another classification is the fabrication technology. That is called the bipolar IC and the unipolar IC. Transistors and diodes are the bipolar devices in which the current flows because of the both of the charge carriers, electrons and holes. All of you know. In the bipolar logic families, the transistors and diodes are used as the key element to produce the ICs. But in unipolar IC, only the MOSFET is used. In unipolar logic families, unipolar devices are the key element. Here the MOSFET is a unipolar device in which the current flows because of only one type of charge carriers, either electrons or the holes. So the examples of the unipolar families are PMOS, NMOS, and the CMOS. So these are the classifications of the generalized ICs. Now the characteristics of the logic family of the digital ICs, which we have to consider to take the particular logic families to design the circuits. The parameters are the V levels and the I levels. V means voltage and the I means current. Speed of operation, that is called the propagation delay. Power dissipation, figure of merit, fan out, fan in, noise margin, and the noise immunity. So first I come to the V level, that is called voltage level. There is 4 types of voltage levels are there. One is called VOH. VOH, that means the minimum voltage level at the output in the logical 1 state under the defined load conditions. Here this is the VOH, output high. VOH means output high. And VIH means input high for the another gate. And this is the output low. Here this is VIH is high, so it is an inverter. So it is the VOL. Similarly, this VOL is connected to another inverter as a load, where the IL is the load current, input load current. Okay, so this is the VIL means input low for this inverter. So the VOH is the minimum voltage level at an output in the logical 1 state under the defined load conditions. VOL is the maximum voltage level at an output in the logical 0 state under the defined load conditions. VIH means the minimum voltage required at an input to be recognized as the 1 logic state, and IL maximum is the maximum voltage required at an input that still will be recognized as the 0 logic state. So it is very simple as like that. Suppose this is a 0. So the output will be high. So VOH will be high, that is logic 1. Now the VIH is the minimum voltage required at an input to be recognized as 1. This is 1, so this is 1. This is 1, so this is 1. Now this 1 will be 0. So that is the VOL max, maximum voltage level at the output in the logical 0 state. So obviously this will be 0. And if this is 0, then the maximum voltage required at an input, that the still will be recognized as 0 logical state. So if this is 0, then it will become as 1. The next step. Next stage will come as 1 and 1, like this. So this is the voltage levels, that is called VOH, VIH, VOL, VIL. VOH is the output high, VIH is the input high, and VOL is the output low, and the VIL is the input low. As similar as the current levels. IOH, the current flowing into the output in the logical 1 state under the specified load condition. IOL, current flowing into an output in the logical 0 state under the specified load condition. IH, current flowing into the input when a specified high level is applied to the input, IIH. And the IIL is the current flowing into an input when a specified low level is applied to the input. Now come to the second parameters, that is called power dissipation. Every electronic circuit requires a certain amount of electric power for its operation. These are the logic level ICs, digital ICs. So for this reason, they are required the low power supply voltage, low supply power supply. So when a power is supplied by an external source, some of it is dissipated in electronic circuits. It is wastage of power across the circuit components and the devices, because this power is lost by the electronic circuits. The requirement of the power is less if the dissipation is less. So for the ICs, low power ICs or the low power design, we should consider the less power dissipation for the low power circuit design. So the power dissipation should be as minimum as possible. Now the third parameter is the figure of merit. The power dissipation of the logic family should be minimum to reduce the power requirements. But if the power dissipation is reduced, then the speed of the operation is reduced. So we should optimize it. Optimize means we should not forget about the power dissipation or should not forget about the delays. We should consider the optimized power and the delay. So for this reason, we should consider the power delay product. So that is called the figure of merit. Hence, the figure of merit is a parameter considered for comparison instead of using the speed of operation and the power dissipation. The figure of merit is a product of propagation delay and the power dissipation. That is called power delay product. It is measured in terms of picojoules, where the propagation delay in nanosecond range and the power dissipation is milliwatt range. So next come to the very important parameters of the logic families and the digital ICs, that is the speed of operation or the propagation delay. The speed of operation of the digital ICs should be very high. That means the propagation delay should be very less. It is specified in terms of the propagation delay. It is the average of the propagation delay time from high to low state and from low to high state. That is called, this is the propagation delay high to low output. Okay, and here this is the low to high. So this is the output from low to high, and this is the output at the high to low. If the propagation delay is the average of the these high to low propagation delay and the low to high propagation delay. So the TPD-HL is the delay time measured when the output changes from the high to low, and the TPD-LH is the delay where it is low to high. This is very much important for any competitive exam, the propagation delay. So the speed power product will be the propagation delay and the average power. So this is very much important. Now this is very much important for the fan out and the fan in of a digital IC. The fan out and fan in. Fan out is the capability of a logic gate to drive the maximum number of similar gates at its output. Suppose a AND gate is taking its output may drive 4 number of same type of AND gates. Then the fan out will be 4. High fan out is the advantageous because it reduces the need of additional gates to drive more gates. Otherwise, there is so many power supplies will be required to drive these logic gates separately. But if the fan out is maximum, then one logic gate can drive another logic gates. So that is very much important. The fan out is nothing but it is specified by the manufacturer and it is provided in the data sheet of a particular digital IC. Exceeding the specified maximum load may cause a malfunction or the circuit will not be able to supply the demand power. Fan out is calculated from the amount of current available in the output of the gate. Here, this is the I. Okay. So calculated from the amount of current available in the output of the gate and the amount of current needed in each input of the connecting gate. So this I0 should be the equal as I1, I2, I3 and I4. Okay, so the DC fan out is which one is minimum? That is IOH by IH or IOL by IL. Which one is minimum? That will be the fan out. Here, this is the fan out is 4. At the end of my lecture of the total logic family, then I will give some problem on the fan out and fan in calculations. That will be very much important for any competitive exams. Fan in of the gate is the number of inputs that can practically be supported without degrading practically input voltage levels. How many number of inputs are there in a single logic gates? For 2 input gates, the fan in is 2. For 4 input gates, the fan in is 4. If you don't know what is the fan in and fan out, so you cannot make the multiple choice question answers. Okay. So this is the fan out. Fan out is nothing but a amount of current available in the output of a gate and the amount of the current needed in each input of the connecting gates. And it will be the minimum of the ratio of IOH by IIH or the IOL by IIL. Which is the minimum, that will be the fan out. And fan in is the how many number of inputs are exist in a single gate. So that is the fan in. Now very important parameters is the noise margin and the noise immunity. The noise is present in all real systems. We should reduce it. So the stray electric and the magnetic fields may induce some noise at an input of the digital circuits, the electric fields and the magnetic fields. Because of the noise, the input voltage may drop, which results in undesired operations. The circuit should have the ability to tolerate the noise signal. This is the logic 1 output and this is the logic 1 input. So the noise high at that point, this is called the noise high. The difference between the input logic 1 to the output logic 1. So this portion of the noise is incorporated. So for this reason, this portion is called the abnormal operation. Similarly, for the logic 0, this is the logic 0 level input, but here the logic 0 level starts. So in between these two, the difference of the input logic 0 to the output logic 0 voltage or the logic levels is called the noise low level. This is the noise high level, this is the noise low level. The noise immunity of the digital circuit is defined as the ability of a digital circuit to tolerate the noise signals. Noise adds the random fluctuations to the voltages representing the logic levels. Already I told, these are the logic levels. These are the high level noise and this is the low level noise. Hence, the voltage ranges defining the logic levels are more tightly constrained at the output of a gate than at the input. There is some abnormal operations are there at the output due to the noise. So the small amounts of noise will not affect the circuit, but if there is a large number of noise are there, then the circuit performance will be affected. The maximum noise voltage that can be tolerated by a circuit is termed as noise immunity. So the high state noise margin, that is called the VNH, is equal to VOH mean minus VIH mean. VOH mean minus VIH mean. That means output high minimum to the input high minimum. That is called the high state noise. Low state noise is the VIL maximum, this level, VIL maximum, and this level is the VOL maximum. So the noise margin will be the minimum of the VNH or the VNL. Which is minimum, that will be the noise margin. Okay, these two equations are very important. So for an example of the noise immunity, the noise signal is superimposed onto the VCC supply voltage as long as it stays above the maximum value, above the minimum value. This is beyond minimum. The input and corresponding output of the logic gate are unaffected. এর উপরে যদি মানে just V on minimum above the VCC, it will be unaffected. But when the noise level becomes large enough, this is the noise. The noise level becomes the very much large enough and the noise spike causes the high voltage level to drop below this minimum level. This is the unusable area. And this is the noise spike causes input pin go to low by force. So if the noise level becomes large enough and the noise spike causes the high voltage level to drop below the minimum voltage level, then the logic gate may interpret this spike as a low level input. So the input will be changed. and switch the output accordingly, producing a false output switching. Suppose the logic input was logic 1, but if the noise level enter into this area below the minimum level of the V1, then the input treated as a logic 0. So then we will get the false result. So that is the effect of the noise. Okay. And then in order for the logic gate not to be affected by noise, it must be able to tolerate a certain amount of unwanted noise on its input without changing the state of its output. So that is very much important. So this is the noise immunity. Now come to the basic consideration or the basic design consideration of the logic family, where we use the diode and the transistors, or the only transistors, or the CMOSes, or the PMOS and NMOSes, etc., etc. So first, all of we know how a transistor is acting as a switch. The transistor is one of the basic elements of the logic families. For this reason, we should first learn the logic families. A transistor as a switch to learn the logic families. In switching circuits, the transistors operate in cutoff or the saturation. In saturation, it will be on, switch on, or in the cutoff region operation, it acts as a switch off. So the cutoff condition is referred to as the switch off, and the saturation is referred to as the switch on. In the cutoff region, both emitter and collector junctions are in reverse bias condition, and only the reverse current flows in the transistor, which is negligible. Both the emitter and the collector junctions are in reverse bias in the cutoff region. So only the reverse current flows in the transistor, which is very much negligible. All of we know. In the saturation region, both the emitter and the collector junctions are in forward bias condition. When the transistor is operated in the saturation region, the voltage across the emitter junction VBE, this VBE is 0.8 volt for the silicon and the 0.3 volt for the germanium transistors. So the value of V sat, this is VC sat, collector to emitter voltage in saturation, is 0.2 volt for silicon and 0.1 for germanium transistor. You should remember to calculate the operations, different types of operations of the logic families. When the input Vin is applied to the transistor is low, Vin as low, that means 0 volt. The emitter junction is reverse biased. Clear? Because this is 0 and this is 0. So there is no current flowing through the collector terminal, is reverse saturation current, which is very much negligible. If we take the KVL, that is VCC minus IC into RC minus V out is equal to 0, then we will get V out is equal to VCC minus IC into RC from this circuit. In the cutoff region, the collector current IC is equal to 0. In the cutoff region, the IC is equal to 0. So if we put here, then V out is equal to VCC. So at the cutoff region, the V out is equal to VCC. When the transistor is operating in the cutoff, the output is equal to VCC and is referred to as logic 1. Okay. So if this is 0, V in is equal to 0, then the transistor is in cutoff region. Okay. The emitter junction is reverse biased, and only the current is flowing is as the reverse saturation current, which is very much negligible. So if we take the KVL, then we will get V out is equal to VCC minus ICRC. So as in the cutoff region, the IC is equal to 0, then we will get V out is equal to VCC as logic 1. Now, if the input V is applied to the transistor as logic 1, that means 5 volt, then the emitter junction is forward biased. Emitter junction is forward biased. So the current flowing through the base terminal, this base terminal is sufficient, and the transistor operates in saturation mode, because this is also in saturation, forward biased. Base emitter junction is also the forward bias, and the collector emitter junction is also the forward bias. So for this reason, this is acts in the saturation mode. So the current flows through the collector terminal, and there is a considerable voltage drop, that is called ICRC, across the collector resistor. So then the V out will be the V sat only. When the transistor is operating in the saturation, the output is equal to the VC sat, and it is referred to as the logic 0, because this is the voltage is 0.2 volt. This is the 0.2 volt for the silicon, and 0.1 volt is for germanium. So that will be treated as logic 0. So this is the basics of the transistor switch. Here the transistor is either on or off, and it is controlled by the input voltage only. Now come to the main topic, that is the logic families. Till now, I already described the parameters which should have in the logic families digital ICs. That is the V level, I level, fan in, fan out, power dissipation, figure of merit, power delay, propagation delay, power delay product, and the propagation delay, and the noise immunity and the noise margin. And also we already learned the basic elements of a logic family, that is the transistor and its switching operations. Now come to the very interesting part, that is the classification of the logic family, where the all types of digital ICs are incorporated. Mainly the logic family is basically classified by bipolar and unipolar, already I told. And this bipolar is again classified by saturated and non-saturated. Saturated will be classified by RTL. RTL means the resistor transistor logic. DTL means diode transistor logic, and TTL means transistor logic. And for non-saturated, that is the Schottky TTL and the ECL. ECL means emitter coupled logic. From the unipolar type of logic family, it is classified as PMOS, NMOS, and the CMOS. All the digital ICs are in these classified groups. So now we should know the ICs. We all know there is some numerical values, some alphabetical letters are there in the body of the digital ICs. Now these letters and the numbers signifies some parameters. We should know this. To design a particular circuit and the parameters of the digital ICs, we should know the nomenclatures. The part numbering scheme for the 74XX00 series, 74XX series logic ICs, not XX00, that should be the 74XX. So that means that is defined by first SN. SN is the manufacturer name. This 74 is the temperature range. This is the HCT. These number alphabetical values signifies the logic series. This 04, this is the device type or the function. Suppose it is a AND gate or OR gate or NOT gate, etc., etc. And this B is the what type of packaging is used to package the IC. The manufacturer, this code normally consists of 2 letters, and this is a code normally used by a given manufacturer. SN is one used by the Texas Instrument. This is an example. The first 2 letters or 3 letters signifies the manufacturer's name. Here this SN is the Texas Instruments, SN. Other manufacturers set their own code. Now this is temperature range. This is indicated by these 2 figures. That is 74 indicates the 0 degree centigrade to the 70 degree centigrade commercially, and 54 military use purposes. So this 74 indicates the 0 degree to 70 degree commercially used ICs and 54 degree centigrade for the military purposes. That means minus 55 degree centigrade to 125 degree centigrade. So 70 degree from 0 degree to 70 degree for commercial, and minus 55 to plus 125 degree for military. This is very much important for any competitive exam. For most applications, the 74 series is perfectly acceptable, and this series will be found in consumer devices. We already used in our lab that 7432, 7405, okay, so 7486, we already used this type of ICs. So you should know the nomenclature of the levels on the IC's body. This 7400, this is the subfamily, the logic series, HCT. I will come to the later section. These are the logic families. Okay. So this is the subfamily. 7400, for example, is the basic series, but there are many other series are there. I already noted down in my lecture. It will be displayed later. So this, the next, the device type. This is the 04. This indicates the device function or the type. For example, the device with 04 are the hex inverters. 7486. This is the XOR. Okay. So this is the nomenclature, what type of IC it is, or the function of the IC. They are the common across the all subfamilies. Now this is the last letter, that is called the package code. This is the package suffix. It is necessary to refer to the manufacturer's datasheets, as these codes vary between the manufacturers. So these are the 7-port series. These are mainly used by the transistor, made by the transistors. Okay, the TTL mainly, TTL logic families. Now if we come to the 4000 series, these are the MOS families. Okay, so here also the HEF 3-digit number signifies the manufacturer's name. Okay, this is the mainly used for Philips chips. The series, that is this indicated by the 4 in the 4000 figure. Here this is, and this is the device type of the function. This indicates the device function, that is 01 or 03, 04, etc. Suppose this is a 4001. 4001 means this is a quad 2 input NOR. Quad 2 input NOR. Okay. And B, this is the output. Previously, the last letter signifies the package. What type of package is used? Here, for the CMOS type, 4000 series type of ICs, the B, the last letter signifies the output. The early devices did not have any output buffering and were lacking in drive. Later versions were buffered, and these chips had the B suffix added in the part number. So this is the buffer. Okay. Now come to the different types of logic families and the basic details of it. We will describe elaborately in the next 2 classes. First, this is the RTL, the register transistor logic. Here the supply voltage is 3 volt approximately, and it first was available in 1962. As the name implies, it is just resistors and the transistors are used. How it will, how the circuit will be designed, I will come learn in the next class. The DTL, this is the diode transistor logic, where the supply voltage should be the 5 volt. And the MECL1, that is the emitter coupled logic, where the voltage should be the minus 5.2 volt. The ECL was the first type of logic IC family to be developed, and it appeared around 1962. Next come to the ECL3, that is called emitter coupled logic, where the voltage range is, that is the supply voltage only. The voltage range is minus 5.9 to 5.2, minus 5.21. This was an improved from the form of the ECL, emitter coupled logic. Very fast, toggle speed up to 500 megahertz, and the chip would run very warm. So this is the disadvantage, but its speed means that it remained in use, because the frequency, the toggling speed is the 500 megahertz up to. So as the frequency synthesizers, where the very fast counters are needed, this type of ICs are used. Now come to the another type of emitter coupled logic, that is the emitter coupled 10K, where the voltage, supply voltage is this, and it is the toggling speed is 125 megahertz. Okay, before this is 500 megahertz, ECL3, but ECL10K is the 125 megahertz. 100K, it is 350 megahertz. But this is the TTL. TTL is the 74XX series, where the supply voltage is 5 volt, which is introduced in 1964, And this technology and its numbering scheme was adopted for many future generations of the logic chip technology. Already I described it. There is different types of 7-4 chips are available. First is 7-4 XS. This is the basic 7-4 logic gates. This is the 7-4 LXX. That means the low power TTL. This L signifies the low power. Okay. And 7-4 HXX. This is called the high speed. H signifies the high speed, which is introduced in 1964. And 7-4S, this is the Schottky type of TTL, 7-4SSX. This form of the TTL was able to offer the operating speed of the around 4 times that of the standard 7400 logic families. Very much high speed. Then the 7-4LS, S for Schottky, L for low power, A is advanced Schottky, low power Schottky, and it is expense for the power consumption of about 22 milliwatt. Then the 7-4LS ALS, that means advanced low power Schottky. Lower power when compared to the low power Schottky, increased speed. Now the 7-4FXS, that is the very fast TTL. While the speed of essentially the same as the Schottky TTL, it provides the speed at around a quarter of the power. And another 2 types, that is called 7-4HC, that is the CMOS. This is the 7-4F TTL, but 7-4HC XX, that is the CMOS high speed, C for CMOS. Okay. And this is the 7-4HCT. That means the CMOS technology with the transistors. Here only the CMOS for C, and here this is the CT. That means CMOS with the transistors are used. CMOS technology and the transistors are used to reduce the power consumption of less than 1 microampere current, but has increased the propagation delay about the 16 nanosecond due to the TTL compatible inputs. This should be the power delay product should be there, and this is the actually current. It should be microwatt. Okay. So the power consumption is less than the microwatt, 1 microwatt, but propagation delay should be less than the 16 nanosecond. So these are all about the basic introduction of the digital logic families. So I hope you all learn about the digital ICs, how the digital ICs will be chosen by seeing the levels on the body of the IC and the different levels of the voltage levels and the current levels of the digital ICs, logic families, and the noise margins, what is the significance of the noise immunity, what is the fan out, what is the fan in, and the different types of ICs using ECL, TTL, DTL, RTL, and the CMOS and the Schottky type of TTL. So if there is any question, please ask me.
It's